Okay, welcome back to another video lecture for Math 13-16, Plane Trigonometry. And in this video lecture, we will be doing a supplemental video for one of the videos in Unit 1, which contained a proof for Ptolemy's theorem. And this video is intended to provide just an alternative proof for Ptolemy's theorem that's maybe a little bit less heavy on the notation, and it has more of a visual kind of feel to it. So because we're focusing a little bit less on the notation, I'm only going to write the things that are absolutely necessary up here. And there would be a way to formalize this and put additional notation on it, but we're just going to focus on kind of what's happening here and try to show this in a more visual way since we've already provided a different proof in another video. So to begin with, we need to recall what Ptolemy's theorem says. Ptolemy's theorem says that if I have a cyclic quadrilateral, which is just a quadrilateral that can be inscribed within a circle where all of its vertices end on a point on the circle, then the product of the two sides across from each other, in other words, the two sides that do not touch, plus the product of the other two sides that do not touch, is equal to the product of the diagonals in this particular type of quadrilateral. So I've labeled several of the angles here, and I wanted to just very quickly walk through some of my reasoning behind why you see that there are only 4 angles here, as opposed to labeling each individual one with a different Greek letter, because we wouldn't necessarily know their measure. Let's focus on the triangle with sides A, B, and E. E is this dotted line here to begin with. And you'll notice that I just called every angle in that triangle something slightly different. So we have delta down here at the bottom, we have gamma up here, we have alpha, which is the first part of this larger angle, and then we have beta, which is the other part of this larger angle. And we don't necessarily know that alpha and beta are equal to each other because we don't necessarily have that this dotted line is a bisector of that angle. Okay, so notice that because ABE is clearly a triangle, the sum of alpha plus beta plus gamma plus delta must very obviously be 180. Next, because we have a cyclic quadrilateral, we know that the sum total of all of the angles in the figure that is a quadrilateral must be 360 degrees. And so if I were to have these other angles, they must at least in some way be equivalent to the sum total of delta plus gamma plus beta plus alpha, but we don't yet necessarily know how. But that's enough to get us thinking. Secondly, we also know that in order for this to be a cyclic quadrilateral, then beta plus alpha, which is the measure of this angle up here in the corner, must precisely equal to gamma plus delta, which is the measure of this angle down here in the other corner. And we have the same sort of situation here. We know that alpha plus delta must equal to gamma plus beta. And that's and we also know that those sum totals have to be 180. Now we could do a large substitution exercise here to prove that they're all the same thing, but I wanted to just use one of the nice geometry theorems from like a high school geometry class to show this. And the theorem states, it's called the chord's theorem, it states that any angle drawn from 2 points along the same chord, wherever that point lands on the outside of the circle, they have to be subtended by the same angle. So what that means is, if you notice, this angle alpha uses this dotted line and this solid line to go to this chord C. So the other angle that goes to this chord C, its sides go to this chord, which is down here. It uses this dotted line and this solid line D. That's another alpha. They must be the same angle by the chord's theorem. They are of congruent measure because this chord is subtended by the same angle everywhere. So we can apply similar reasoning to all the rest of these. Notice that beta uses these 2 lines to go to chord D, so the other angle that uses 2 lines to go to chord D must also have beta as its measure. We have delta, which goes to chord B. The other angle that goes to chord B is also delta. We have gamma, that goes to chord A. Gamma goes to chord A. Okay, so in this way, since we know the sum total of delta plus gamma plus beta plus alpha is equal to 180, we can show that our quadrilateral follows the rules for quadrilaterals. In other words, all of those angles sum to 360. And furthermore, we could do some exercises to show that this fact is true as well. But what we want to do now is start cutting some triangles out of this thing to get on with the rest of our proof. So the first thing we're going to do is we're going to cut the triangle with sides B, C, and F out, and we're going to rotate this thing upwards. And I'm doing kind of a bad job of preserving the exact shape of that triangle, but keep in mind that this is just a general cyclic quadrilateral, so these triangles change their shape just based on the specific angle measures that we have in this thing. So it's okay if they look a little bit different. We're just trying to make a point here. So we take B, C, and F, and we make it so that side B lands here, side C is up at the top, and side F is in the middle. So next we cut triangle ABE, and we're going to arrange it in such a way that side E is along the bottom. And just tilting it down like this, we'll have side A here, and we'll have side B here. Then lastly, we're going to cut the triangle labeled AFD, which is AFD, and we're actually going to flip this entire triangle almost 180 degrees so that side F goes right here. And then remember, we flip this thing over quite a bit. That makes side D go along the top, and that makes the last part side AFB over there on the right. But next notice that there's a whole bunch of different sides, and my goal here is to kind of slap these three triangles together into a parallelogram. But I can't do that because you notice that F might be of different measure than A, which might be of different measure than B, which of course B might not be equal to F either. So what I have to do is I have to scale these triangles by something to make F equal at least to A, or it has been scaled in such a way that it is, and then make F equal to B, or at least it has been scaled in such a way that it is. So you notice that we could just look at this, and if this triangle said AF for this side, if we scale this whole triangle by F, this would be AF, this would be BF. So then both of these triangles have the F part of that matching with that triangle in the middle. It's just that this triangle is missing a scale factor of A, and this triangle is missing a scale factor of B. So let me draw that parallelogram real quick. I'm going to do my best here. I want this to be usable. So there's some point up here at the top that connects to that vertex, and that connects to that vertex. And since we scaled this triangle, which was originally this triangle, by F, we have FE on bottom. We have BF on this right side. We have AF on this left side. And then we remember this triangle was scaled by A, so this will be AB, and this one will be AC. Then we have this triangle over here. I'm going to erase E real quick just because I'm running out of space. This triangle was scaled by B, so we'll have BD, we'll have BA, which is of course AB, and then we'll also have BF like that. Okay, so we can already kind of see that this parallelogram figure is probably a parallelogram because we have at least these two sides here that are of precisely the same measure. But in order to show that this is a parallelogram, we must show a couple of things. First off, we have to have two parallel sides, two sets of parallel sides that have the same measure. And to do that, the easiest way that we can concoct is to show that opposing angles, meaning this angle and this angle, are congruent, and this angle and this angle must be congruent. Well, to do that, we can simply look at how we constructed the parallelogram out of which triangles on our original figure. And we want to remember that a dilation preserves the angles of the figure that it is dilating. So when we scaled each of these triangles, we didn't change any of the angle measures. Now on this first triangle, it was the sides B, C, F, and we recall that this point up here ended up being all the way down there. All right, so BCF had this angle here, alpha. Over here we had the angle delta. And then right here, this is this thing up here, this is gamma plus beta. Gamma plus beta. Okay, well then we had triangle ABE, and we just kind of sat this thing down. So what we notice is that this angle here is just this angle right there, ABE. That's gamma. So this is gamma. Next we have that this thing right here. This is the angle over here. This is delta. And what's left over on triangle ABE is beta plus alpha up here at the top. So this was beta plus alpha up here at the top. And I know that's going to get a little hard to see because the figure's kind of small. Okay, well the last part of this is probably the most confusing. We took triangle AFD and we gave it a total 180-degree rotation. So this angle right here actually kind of ends up at the top of our triangle. Another way to think about this is that when we rotated this 180 degrees, this angle ended up down at the bottom. So beta actually ends up right here. And that may actually be all we have to show, because notice that this angle right here is gamma plus beta explicitly, and then this angle is gamma and this angle is beta. So this angle and this angle have to equal each other because they are both gamma plus beta. Well, if we continue here, you'll notice that up at the top that we have delta plus beta plus alpha, and this thing right here will ultimately, in order for this to be a parallelogram, we simply have to make sure that it is the missing angle gamma. So notice if we have rotated this thing up, this angle here rotated is actually going to end up in the top left of that figure, so it is precisely gamma. So we can prove that this whole thing right here is in fact a straight line, because we have delta plus beta plus alpha plus gamma is 180 degrees, so that is a straight angle in total. We'll notice that if we have beta and gamma here, then the only thing that we're missing out of this triangle is alpha plus delta, because all of the triangles were composed of the same types of angles. So this is just alpha plus delta. And now notice that the other opposing angle, alpha plus delta, is alpha plus delta, beta plus gamma is beta plus gamma. So we have our parallelogram. Then notice on a parallelogram, these two sets of sides must be equal, which means these two sets of sides must be equal. So to get the total length of this top side, we have the statement AC plus BD equal to, then we have this bottom side EF. But that's precisely the statement of our theorem. Notice that the product of side A and side C plus the product of side B and side D is precisely equal to the product of the diagonals E and F. And that is the proof for Ptolemy's theorem.